The last session we started this topic. The main topic is chemical reactions, and the subtopic is about rate of the reaction or speed of the reaction. So, if you want to calculate the speed or the rate of a reaction, what we can do, we can measure the amount of the product or amount of reactant the change divided by time will get the rate. And the last session we have discussed is that the rate of the reaction can be affected by concentration, the size of the particle, the temperature, as well as the catalyst. And the last we were discussing was about the catalyst. So what are catalysts? Catalysts, the substance which alter the rate of the reaction, we call that as catalyst. And so the catalyst is the substance which alter the rate of the reaction without chemically used or consumed. So amount of the catalyst does not change throughout the experiment because it's only speed up the reaction, but it does not take part or does not add to a reactant mixture or not changing the amount of a product. Then catalyst can be a normal catalyst, or it can be biological catalyst. So a catalyst can be refers to a normal catalyst or it can be a biological catalyst. A normal catalyst, it work at all the temperature. But biological catalyst, it will work as a catalyst at certain temperature. And the biological catalyst having a name, specific name, what we call biological catalyst, we call them as enzymes. So a catalyst is a substance which alter or change the rate of reaction without chemically used. And catalyst can be divided into a normal catalyst or a biological catalyst. Normal catalyst means that it will work at all the temperature. But biological catalyst means the catalyst which will work at a certain temperature, a certain range of a temperature, and after that it does not work. So we call them as biological catalyst. So example, if we want to convert a sugar solution into alcohol, plus carbon dioxide. This is a chemical reaction that when we have a sugar solution, a solution can turn into alcohol and carbon dioxide. But what happened? The reaction is very slow. Say this is a sugar solution. Or you can say glucose, and it decomposes into alcohol and carbon dioxide, but the reaction is very slow. The reaction does not take it take too much time to complete. So what we do, we add a yeast, a substance. Yeast is added. Yeast is having enzymes which are biological catalysts. So when we add the yeast, the addition of the yeast, it is speed up the reaction. So a sugar solution can decompose into alcohol and carbon dioxide, but the reaction will be very slow. In the presence of the yeast, the reaction speed up, so it can occur at a faster rate relatively. But what happened? Example, we have a sugar solution and we add a yeast. So sugar solution, we add yeast and the reaction speed up. But for example, it was working fine when the temperature is 30. But when we supply the heat energy and the temperature of the mixture rises to 50 degrees centigrade, what we observe that the reaction slow down. So why the reaction slow down? Because yeast, which is a biological catalyst, so yeast is a biological catalyst. So at 30 degree it was working fine, but at 50 degree it is not working. So when the catalyst is working at a certain temperature, what we call that catalyst, we call that as biological catalyst. Is it clear the concept of, so most of the biological, almost all of the biological catalysts are organic molecules. Is it clear the concept of biological catalyst? So catalyst is a substance which alter the rate of a reaction. A catalyst can be biological catalyst or it can be a normal catalyst. So example, when nitrogen reacted with hydrogen, so when nitrogen is reacting with hydrogen, it form a gas which we call ammonia. And the substance which we use a catalyst here, we use iron as a catalyst. For example, if we use 2 gram of iron, it can be any number, but we use 2 gram of iron. So when we carry out the reaction at 400 degrees centigrade, the iron was effective, it was changing the rate. When we carry out reaction at 450, iron was effective, it was affecting the rate. When we carry out at 500, iron is still effective, it is carrying out affecting the rate. When we carry out at 600, iron is still effective and it is affecting the rate. So when the catalyst, the substance which is used as a catalyst, it is working at all the temperature, what we call this, we call that as a normal catalyst. But if it was a biological catalyst, like example, if it was a biological catalyst at certain temperature it will work, and after that it will stop working. So at 500 and 600, if it does not work, it means it was only working at certain temperature and other temperatures it's not working, so we call that as biological catalyst. But in this example it's not a biological catalyst because iron is working or acting like a catalyst or altering the rate at all the temperatures. And amount of the catalyst before and after, like example, if in the beginning if we have 2 grams of the catalyst when we start the reaction, so when the reaction finish after, it will also be 2 gram. So amount of the catalyst does not change or it remain same, because catalyst is not the reactant, catalyst is not the product, it is only a substance. When we add to a mixture, it speed up the rate of reaction. So simple experiment to find, this is very important. So experiment to find whether substance is a catalyst or not a catalyst. So experiment to find substance whether it is a catalyst or not a catalyst. For this purpose, what we use hydrogen peroxide. Hydrogen peroxide is it's a chemical which can decompose by itself into water and oxygen. The chemical formula for hydrogen peroxide is H2O2. So hydrogen peroxide, it is H2O2. When it decomposes into water, H2O, and oxygen, which is O2. The equation must be balanced, so we balance oxygen and hydrogen. This is a balanced equation. That hydrogen peroxide decomposes into water and oxygen by itself. Whenever we know hydrogen peroxide is a liquid, so state symbol L. Water is a liquid, state symbol S, L. But oxygen is a gas, so state symbol will be G. So whenever a gas is given off, we will observe or see bubbles. That is what we observe or see whenever a gas is given off. So how we can tell whether a substance is a catalyst or no? So whenever we want to find a substance is a catalyst, we use this hydrogen peroxide. Like example, we take a conical flask and we fill this conical flask with hydrogen peroxide. This is representing hydrogen peroxide. And we know this hydrogen peroxide give off oxygen. So we can connect a gas syringe here. A gas syringe is used to measure the volume of the gas. So at this point, a gas syringe is connected. And we'll measure the volume of the gas given off when hydrogen peroxide is decomposing without catalyst. The first one is without catalyst. So without using a substance as a catalyst, we just find how much oxygen is given off in a unit time. And whenever we are working out the rate or speed of the reaction, we should always have a stopwatch, because rate is always calculated with reference to time. So we'll measure how much gas is given off with respect to time without a catalyst. After that, say this is a substance X, and substance X, we want to find whether substance X is a catalyst or no. So what we will do, we will repeat the experiment. We'll take conical flask, we will fill this conical flask with same amount of hydrogen peroxide. The blue is representing the hydrogen peroxide. And this hydrogen peroxide, this time what we do, because we want to find whether this substance X is a catalyst. So we will take this substance and we will place in a conical flask. So substance X is placed in a conical flask. And then we'll connect a gas syringe and after connecting this gas syringe, we'll measure the volume of the gas given off. Like in 5 minutes or 3 minutes, same like the first. If first experiment is done for 3 minutes, the second experiment should be done for 3 minutes as well, so that we can compare. So if first experiment is done for 3 minutes, we measure the volume of the gas. The second experiment should also be done for the same time interval. If substance X is a catalyst, so in the same 3 minutes, what we will get, because a catalyst speed up the rate of the reaction, so in the same 3 minutes, we'll get more volume of the gas. And here in 3 minutes, we'll get less volume. So without a catalyst, the reaction is slower. That's why smaller amount of oxygen is given off. With a catalyst, the reaction is faster. So in a same time interval, greater amount of the gas is given off. So using this idea of hydrogen peroxide, we can identify whether a substance is catalyst or not. So if the substance is not a catalyst, it will not alter, it will not change the rate of reaction. It will, with catalyst or without catalyst, it will be same. But if substance is acting like a catalyst, it means that it will give a greater amount or greater volume in a same time interval. Is it clear how we can work out that whether substance is a catalyst? Any doubt in this part? A simple experiment to identify whether a substance is a catalyst or no. So always remember, we use hydrogen peroxide. It's a lab chemical which decomposes into water and oxygen by itself. By absorbing the heat energy from surrounding, it can decompose. But it's a very slow reaction without a catalyst. But with a catalyst, it's a fast reaction. So we'll see rapid bubbles or greater volume of the gas in a unit time. Then there are certain reactions which are affected by light. So the reaction which is affected by light, we call them as photochemical reaction. So what is a photochemical reaction? Photochemical reaction is the reaction, the rate is affected by the light. And the best example to understand the photochemical reaction, that is photosynthesis. Photosynthesis is a photochemical reaction. What are the reactants in photosynthesis? What happened? Like we have water and carbon dioxide. When they combine with each other, it gives off glucose plus oxygen. So if we have water and carbon dioxide, if we have more water and carbon dioxide, it means we have more reactant particles, so reaction should be faster. But in reality, it does not happen like this. Even if we have more water and carbon dioxide, the reaction will not proceed unless what we have light. So without light, this reaction cannot proceed. Without light, this reaction cannot occur. So the reaction which cannot take place without light, what we call them as photochemical reaction. So photosynthesis is one of them. That what happened when the light falls, a green plant having chlorophyll, so they trap this light, and a chemical reaction between water and carbon dioxide leads to a formation of glucose and oxygen. And it does not occur without or in the absence of the light. The photosynthesis cannot occur. That's why during a daytime the plants are releasing oxygen. Why? As they absorb the light energy, combine water with carbon dioxide, result in a formation of glucose. There is also another reaction, photochemical reaction, that is photographic film or photographic plate. The photographic plate or photographic film reaction is also a photochemical reaction. What happened in this? Now it is not common, the photographic plates, but now we have digital cameras and mostly we are using mobile, but the old cameras which use these photographic films, I will show that how it appears. Maybe you have seen this. It's not common right now. This is a photographic film. It was used in old cameras. Now in digital cameras are not having any kind of film. It's just use a memory, but this is a photographic film. So what happened to this photographic film? This photographic film is actually silver chloride AgCl. It's having a layer of silver chloride. So when the light falls on silver chloride, it will form a silver metal plus chlorine. So what is the effect of the exposure or effect of the light on the photographic film? This is also a photochemical reaction. It only happen in the presence of light. So reaction which can take place only in the presence of light we call photochemical. So what happened originally, it is light brown in color. The photographic film is light brown in color. But when it is exposed to the light, and it is having a layer of silver chloride. So this is silver chloride. But when it is exposed to the light, the point where it is exposed to the light, due to the light, the silver chloride turn into silver and chlorine. And silver will make it gray, or we can also say black. So the part where it is exposed to the light, that part will become black. And greater the light intensity, if a small amount of light falls, that part will be gray. If no light falls on that region, it will not change a color. So the light caused the silver chloride to turn into silver, and the part where like the part of the film which is exposed to the light, a greater amount of light intensity, that will turn to be black. The part which is exposed to smaller amount of light, that turn into gray, and the part which is not exposed to the light, that will remain as it is. So as you can see here, this is a photographic film, photographic plate. So you can see, we can identify different shades. So what does it mean? Here it appeared to be completely dark. So it means if this side appeared to be completely dark, what does it mean? It means more reaction, or this part is exposed to greater amount of light. So greater amount of light intensity is there for this part. And the part which appear to be light in color, like example, you can see this part or even this part, it appeared to be light. So what does it mean, or lighter? It means small amount of light falls on this region. So this is how the photographic film develop, like it create an image. So a flash produce a light, the flash from the camera produce a light, and that light reflect from the object, and it enter the camera and expose the photographic film is exposed to the light. So some region there will be too much light, so that will become dark, and some region small amount of light is there, so that will turn to be lighter. Is it clear, the concept of photography and photographic film and old cameras and photosynthesis? Any doubt till this point? So if you want to measure the rate of the reaction, there are different ways to measure the rate of reaction. What we can do, if a chemical reaction involve a gas is given off. So when gas is given off, we can use this apparatus, we can measure the, both of them are valid to measure the rate of the reaction. But in this one, in which we connect a gas syringe, what we'll do, we'll measure the volume of gas in unit time. And here what happened, if a chemical reaction produces a gas, so what we do, we place a cotton wool. So when we place a cotton wool, it means we allow the gas to escape. So the gas will escape. And what is the purpose of the cotton wool? The content of the flask should not escape, only the gas will pass through the cotton. So when the gas will pass through the cotton, what will happen here? The mass of the content will decrease. So how we measure the rate? We'll measure the change in the mass. We'll measure the decrease in mass in unit time. So example, I will give example for both. Like if you are measuring a volume of a gas, and both are valid when the gas is given off. A chemical reaction in which a gas is given off, we can use any of these techniques. The first technique will measure the volume of the gas, and the second technique we allow the gas to escape and we measure the change in the mass of the content and the flask. So example, if we are using the first technique, so how the results will appear if you are using the first technique. Because the gas, the volume is a product here. So in the beginning, you don't have any product, so it will always start with 0. Here we have volume of gas given off. Example, it is in centimeter cube. And the second one is a time. It can be second, it can be minutes. It depends on the question. So in the beginning, at the start, when time is equals to 0, there was no gas given off, so we write 0. When time is, example, 2 minutes, we got 20 cm cube of gas. When time is equals to 4, we got 35 cm cube of gas. When time is 6, we got 38 cm cube of gas. When time is equals to 8, we also got 38 cm cube of gas. So in the beginning, the amount of gas is given off at a faster rate because more reactants are there, but with the passage of the time, the amount of the gas, the change in amount of gas is decreasing, and until it is constant. So when the amount of the gas is constant, it means the reaction stops. How we can calculate the rate from A to B, from B to C, from C to D, and D to E? So what is the rate of this reaction from A to B? What is the rate? The change in amount divided by time. So what is the rate here? So it will be 20 minus 0 divided by 2 minus 0. So 20 divided by 2, that's equal to 10. And what is the unit? According to this, it will be centimeter cube per minute. What about the rate from B to C? So 15 divided by 2, 7.5 centimeter cube per minute. What about from C to D? 38 minus 35 divided by 6 minus 4. So it will be 3 divided by 2, which is equals to 1.5 cm cube per minute. And from D to E, it is 38 minus 38, which is 0, divided by 8 minus 6. So it will be 0 divided by 2, 0 centimeter cube per minute. So the rate of the reaction always decreases. In the beginning, you have more particles of the reactant. That's why the fastest in the beginning. But with the passage of the time, the rate is decreasing. So when we sketch a graph for volume of the gas and time, so in the beginning, we have 0, and with the passage of the time, the rate it is steeper. In the beginning, it's faster, then slow down, and eventually it will be 0. So this is how the results will appear if we are collecting the gas given off during a reaction. Is it clear, this concept? The second part, how we can use the second technique to measure the rate. In the second technique, because we allow the gas to escape, so the mass will decrease. So mass of the content in the flask, in the beginning it will be greater, higher value, but with the passage of the time, the content of the flask, the amount will decrease. So mass of content and time, it can be second, and mass of content can be in gram. Say the originally in the beginning, the mass of this content at the start of the reaction, it was 200 when time is 0. Then it changes to 140 after 2 seconds. Then it changes to 120. Then it changes into 110. Then it changes into 108. And then 108 and 108. Why the content of the flask, as you can see, it is decreasing, but I did not write the mass of the content will be 0. Why I cannot say mass of the content is 0? Because when even the gas is escaping, when the gas escapes, still some of the substances will be there which are in the liquid state or a solid state. That's why the mass of the content will never be 0, because it will decrease, but it won't be 0. As the flask itself, the conical flask itself is also having its mass. So when we measure the rate of the reaction for this type of reaction, so measuring a rate from A to B, the change is how much? 200 minus 140, and the time interval 20 minus 0. So it will be 60 divided by 2, that is equals to 30 gram per second. When we calculate from B to C, 140 minus 120 divided by 4 minus 2. So it will be 20 divided by 2, that's equal to 10 gram per second. From C to D, it is 110 minus 120 minus 110. divided by 2, so it is 10 divided by 2, which is 5 gram per second. Then from D to E, it is 110 minus 108 divided by 2, the time interval. So it is 2 divided by 2, 1 gram per second. And the last part, because there is no change here from E to F and F to G, so the rate will be 0 gram per second. And when we sketch a graph for this result, so we have mass and time. In the beginning, we have like 200, and then it changes to 108, and it will be constant. So this will be the shape of the graph. Why I did not intersect to x-axis, why I did not draw like this? As you can see, when the gas escapes, still some of the content are still in the flask, so they will have the mass. That's why the total mass cannot be zero. Even the container, the conical flask, it's having its own mass. Is it clear, the concept, how we can work out the rate of a reaction when a gas is given off? So this is another way of measuring the rate. Then another experiment is there, how we can measure the rate for when a solid is formed. I'll share another link and continue this discussion.